Now let's begin talking about the superposition principle. So if we have any function f of x, and if this f of x, of course, satisfies the boundary conditions of whatever problem we're talking about, and for particle in a box, our boundary conditions were that psi of x had to be 0 at the endpoints of the box. But assuming that this function satisfies whatever requirements we put on our wave function, any function f of x in one dimension x can be represented in the following way. We can represent it as a sum from the integer n equals 1 all the way up to infinity, however high n goes, as a sum of a coefficient, just some constant number, times the nth wave function, the nth eigenfunction of the Schrödinger equation, then psi of x, and then the sum of those up into infinity. So in this case, what we're looking at here is what we're going to be calling a basis set. That this function f of x here can be represented in terms of the set of these functions psi n of x. Now, an example of a basis set you're probably familiar with is if you've studied Taylor series in calculus. Taylor series is taking a function like a sine, exponential, any function you want, and you're expressing that function in a basis set of polynomials. So you know that the exponential can be represented in the basis set of polynomials as 1 plus x squared over 2 plus x cubed over 6, etc. So we can represent any given function, which could be any possible wave function, as a linear combination of our eigenfunctions here, and our eigenfunctions are going to be the basis set for expressing this function. So this is going to be a very important relation for us going forward, that we can do this. And if we want to do this in terms of the type of Dirac notation which we've been introducing lately, we can say that the function f can be represented as a sum from, I keep putting I down here, but I mean n, from n equals 1 to infinity of Cn n. Function n equals psi n of x. And then, as I said, we're calling the set of all the eigenfunctions are called a basis set, as I have up in the title. Okay, so if we want to go about figuring out what these coefficients are, so let's do something. Let's take some function m, so this would be fm or psi m star of x, and then we're going to integrate, we're going to multiply that times f and integrate from 0 to infinity, from negative infinity to infinity. This is the type of Dirac notation integral which we introduced previously. So this, if we represent our f as this type of a function, is going to be sum from n equals 1 to infinity of, well, these cn's are just going to be constants, so we can pull them out in front of the integral. So we can just have mn. But then these mn, we know that these are eigenfunctions of the Hamiltonian. And the Hamiltonian, because of postulates of quantum mechanics, we know is a Hermitian operator. And we showed that for Hermitian operators, the eigenfunctions are orthogonal. So let me just go down here with this. So I'm going to write a little bit more. For m, the integral of mn n fm star psi m star of x times psi n of x integrated from minus infinity to infinity, that is going to equal what we're going to call this Kronecker delta, which we're going to use a lot moving forward. Kronecker delta mn. So this function delta mn equals two possible values. It equals 1 if m is equal to n, so delta 1 1 equals 1, delta 2 2 equals 1, etc. And if m is not equal to n, it's 0. So this is a way you can represent functions which are orthonormal to each other. So we have that the set of all of the eigenfunctions, which are our basis functions, are orthonormal. As we showed in the previous video, they are orthogonal to each other, and they are also normalized because if I have n here, it equals 1. So this is called being orthonormal. They are both orthogonalized and normalized. Okay, so using that, then up here we have that this sum from n equals 1 to infinity times Cn. This integral here is going to become delta Mn because these are orthonormal functions. And now, for the last part, this sum from n equals 1 to infinity, for any given m, there's only going to be one case where n equals m. M has a specific numerical value, and maybe it's 5, maybe it's 10, maybe it's 100. But there's only going to be one term in the summation where n equals the same number as n. And whenever it does, it's going to equal 1. So whenever we have Cm times delta Mn, we're going to have a 1. So the only value for which this term isn't going to go to 0 is when n equals m and we get Cm back. So in fact, we can see from this that this is going to be a way for us to get what these coefficients are. So for example, if we have some given function like, I don't know, x squared or e to the x or any function we want, and we have some basis set of eigenfunctions that we can find out, we can represent the function as a sum of these eigenfunctions times a coefficient, and we get the nth coefficient by multiplying our function times the nth eigenfunction and then integrating from minus infinity to infinity, and that'll give us the coefficient for that individual basis function there. So then putting this all back in terms together, what we have is that the function f equals the sum from n equals 1 to infinity of Cnn, and that this set of Cn's are equal to, I'm going to put the function n first this time, that this Cn is equal to the integral of n times f integrated from minus infinity to infinity. But you see, by this form here, we have that f equals something times f. And because we end up getting f back here, what we can say is that this whole thing, if we picture it as an operator, this sum from n equals 1 to infinity, it looks like this, that when we multiply this times f, it's going to give us every integral from minus infinity to infinity of psi n star of x times f of x, and then this resulting value is going to be a coefficient, and that coefficient is going to precede the basis function, and then all of the basis functions together form the whole complete basis set for representing this function. So in fact, if we factored all of this out, we would just get the function back. So this operator here is equal to an identity operator, where we said that an identity operator acting on a function f of x just gives the function back. So this type of operator doesn't actually change the function at all. It's just a way of getting the function into a different basis set. It tells us what the coefficients are for the basis set of this function represented in that basis of those eigenfunctions. Okay, and then this type of operator here, which I have in there, that's something which you might hear referred to as a resolution of the identity. So identity being that the whole thing is equal to an identity operator here, but the resolution refers to resolving this function f of x into what its coefficients are in the basis of these eigenfunctions. So this all seems very, very abstract right now and perhaps somewhat obtuse, but in the next two videos we're going to show how this is really, really useful for figuring out the types of values you get when you want to measure things like energy or position, and also do a practical example to see how it's useful for a specific situation.